Okay, this is the final discussion. Thanks for making it all the way through. I'll be having one more session tomorrow, 6 to 8 p.m. in Camper. But for now, we're going to finish week 10. And I have 5 problems prepared for us. Some involving Moody flow chart with the reflective pipe flow, so kind of like the turbulent flow stuff. And I also have laminar flow through pipes as well. And those are the different 5 problems we'll cover. Let's get started. So the first problem, we're given that there's a liquid specific weight. We're given that specific density, flows via gravity through this pipe setup. It is, so half of it, the first top, 1 foot height of tank. Second half, 1 foot height for the tubes. And we're given that there's a volumetric flow rate, 1.15 cubic foot per hour. And we're saying both conditions 1 and 2 exposed to atmosphere. We're going to neglect entrance effects of friction as fluid from the top tank is getting sent to the pipe and out. And we're interested in finding the viscosity of the liquid. So viscosity, when we think about in simple layman terms, it's kind of like the friction term for the fluid flow. And if we were to neglect those effects in the large tank, obviously the effects is going to only come into play as the fluid is moving through the pipe in the bottom half of the setup. So just to read it one last time, the top half we're going to treat as a reservoir, kind of like back in hydrostatics. Second half we're going to treat as pipe flow problems that we've been currently seeing. Okay, let's write down our givens. So we're given specific weight, 58 pound force per cubic meter. We're also given height of the tank and height of the pipe, both being 1 feet. We're also given diameter of the tube, or pipe, 0.004 feet, and volumetric flow rate, 0.15 cubic feet per hour. So, we're interested in finding mu. And I said earlier, mu is only relevant for the pipe flow. With all these terms, I guess, where should we start? We have rho, g, we have q, but we don't have mu. So we can't really solve for Reynolds number. And that's important because Reynolds number is how we determine if the flow is laminar or turbulent. Therefore, I'm going to make the executive decision to make the assumption that our flow is laminar. I'll talk more about that in the following problems, but for now, we're going to assume laminar flow. So, what does it mean when I say laminar flow? A big part of that is that our h of f term gets simplified. Yeah, yes, Marvin.
Why are we assuming laminar flow?
So, like I said, this could be an executive decision I make now. Basically, there are key terms and details that I look at when I make these. When I either assume laminar or turbulent, they'll be more relevant in the next problem when I'll talk about that. But for now, I'm gonna say laminar flow, and it's because I was not giving enough information for Reynolds number, for the time being. And so usually, the general expression for h of f, or head loss, is Darcy friction factor times L over d times velocity head. However, in the laminar flow region, we can express Darcy friction factor as the following. In laminar flow, it is 64 divided by Reynolds number. Therefore, substituting this expression into my equation, head loss comes out as 32 rho, or mu, LV divided by rho g d squared. Sorry about that, 1 second. Hey, I'm in class right now. Can you wait? Okay, just stay at the arc and chill around. I'll see you in a bit. All right, sorry about that. My cousin's coming up from San Jose. All right. So this is our expression because obviously we can express f as this function or variable. I break it Reynolds number down to its terms. I get the following equation, and this is the laminar equation, which you've seen in the quiz and in class, I believe. Okay, and I'll talk more about this next problem as well. I'll talk more about that then. Back to the problem statement at hand. We have friction, or f of f, and I'm gonna hold on to that for now, because technically we have our unknown of mu. We don't know what mu is. And we also don't know what h of f is. So we need a second equation to solve for two unknowns, because two equations, two unknowns, right? So the second equation we're going to rely on is energy equation. Based on locations 1 and 2, we can then apply the energy equation to correlate the two expression and term and basically obtain another expression with h of f. An energy equation is as following. It's internal energy term plus kinetic energy term plus potential energy term, same on both sides, plus head loss minus pump work plus turbine work. So in our setup, obviously, with a reservoir and pipe, there is no pump, there's no turbine, but there is some kind of head loss occurring, as we mentioned earlier in the pipe. We mentioned earlier that both sides is exposed to atmospheric pressure. Therefore, the internal energy terms cancel each other out. We're told that, the top part, I said, treat as a reservoir in hydrostatics. Bottom part, that's pipe flow. So, because top part is kind of like a hydrostatic reservoir, there's no flow occurring. Finally, last thing we're going to do is set the ending or the bottom of the pipe to be datum. That's location 2. Set location 2 to be our datum. If we set location 2 as datum, datum basically means that is where the z is equal to 0. And if z is equal to 0, you cancel that term out. So our expression simplifies to the following. Z1 equal to velocity head at the exit plus head loss, which we substitute in later. But in terms of V, which is the velocity of fluid going out, we're given volumetric flow rate. So obviously that's the flow rate exiting our system. With the cross-sectional area, we can solve for velocity. I'll probably need another page for that. So V is Q over A. Q is 1.15, and I'm going to divide by this to get cubic feet per second. Divide by area, pi over 4 times diameter, 0.004 feet squared. This would give me a velocity of 3.316 feet per second. And its value is, this is going to be used as equation because I want to solve for h of f. C1 minus alpha V2 over 2g squared. Okay, let's talk about the alpha term. Alpha term, I mentioned before, that's the kinetic correction factor, and it's important because we can't assume flow going through a pipe to be 1D. Essentially, we can't assume that all the fluid passes through that cross-sectional area at the same time. There is Poisson's Poisson-Wells flow, and that's the parabolic profile. Therefore, obviously, the center line velocity is going to enter first before the other velocities of that system. So when you take the average of the velocity, that's one thing we can do. That's the V term, but we also need to apply the kinetic correction factor. So for laminar flow, your alpha will be equal to 2. For turbulent flow, alpha is equal to roughly 1. So remember earlier, we made the assumption that our flow is laminar. Therefore, alpha is equal to 2. Just something to keep in mind. All right, let's plug in our variables. Z1, height of the tube and your reservoir, that's 2 feet, minus alpha, which is 2, times V, 3.316 feet per second squared, divided by pi over 4, 2 times G, that for VG units, that's 32.2 feet per second squared. Therefore, head loss is equal to 1.66 feet. And that's important because now we're going to plug it back into this expression to solve for mu. Head loss for laminar is equal to 32 mu LV over rho GD squared. To solve for mu, take every other term, take the reciprocal, multiply it over. Rho G D2 32 LV H of F lam. So I'm plugging into relevant terms. So I get specific weight, 58 pound force per feet squared, times velocity, times G, times D squared, 0.004 feet squared, divided by 32 times L. Remember, L is fluid pipe length of the pipe length which the fluid travels through. The fluid does not travel in the reservoir, it only travels through the pipe. The pipe is 1 feet long, therefore L is 1 feet, times V. 3.316 feet per second. Head loss height, 1.66 feet. Therefore, mu can come out as 1.45 times 10 to the negative 5 pound force times second per feet squared. And this is just basically in terms of pressure times second. That's the unit for viscosity. So I initially had one equation, two unknowns. I introduced a second equation, so I had two equations, two unknowns. I could solve for both. And remember, initially we made the assumption that the flow is laminar, right? Now we have to double check the expression. Otherwise, we basically solved a different problem. And you're gonna lose a lot of points from that. So let's check Reynolds number. Reynolds number for pipes is rho v d over mu, which is the same as, so 58 divided by 32.2. This will get you down to rho, which is slugs per cubic feet, velocity v, which is 3.316 feet per second, times 0.004 feet divided by mu. 1.45 times 10 to the power negative 5. That's feet per second, feet squared. Therefore, Reynolds number is going to be equal to 1,650, less than critical number. Therefore, our assumption is valid. We got the solution, and our assumption matches up. So we're good. Any questions on that process? If not, go to next problem. Next problem, oil. And we're given the oil property, which is density. And we're given, this is dynamic viscosity. Dynamic viscosity is just, dynamic viscosity is just mu, kinematic viscosity divided by rho. It's just another expression for viscosity. And both refer to friction or dissipation, basically just losses in your system. We're given volumetric flow rate. Oil is flowing at 0.2 cubic meters per second through a 500 millimeter pipe with a 200 millimeter diameter, so which is just 0.2 meters, of a cast iron pipe. And for now, that's all the information we need. Okay, so first we want to find head loss. But before that, I want to point out that in this problem, they gave us something about the pipe characteristics. Pipe, basically what is either what's made out of, or they give us how rough it is, which is epsilon. When I see any of those two terms pop up, it gives me a feeling or an urge that we're most likely working with turbulent pipe problem, because usually this information is not necessary for laminar flow. But when I see this information, I think I have a feeling that's going to be a turbulent flow. So I'm not going to make the assumption that we're working with a turbulent flow. Once again, is due to this information of, they said it's a cast iron pipe. Yes?
Would changing pressure also entails turbulent flow, or does that not?
You're saying pressure difference?
Yeah.
Because pressure difference is needed to drive a flow. So even laminar flow needs pressure difference to even, to have velocity. Otherwise, there'd be no velocity. So yeah, at least for me, it's the detail of the pipe. So part A, head loss, H of F. Once again, H of F, the general description is F times L over D times velocity head. Head loss. Let's solve for terms of interest here. LD we have, that's just pipe geometry. V, which is part of the flow characteristics, we solve through Q. So 0.2 cubic meters per second. By area, pi over 4 times d squared. The math will come out to be 6.366 meters per second. That's my velocity. So, once again, I have basically every term here but F. F being referred to as Darcy friction factor. I mentioned this in last class, but do you remember how I said Darcy friction factor is a pi group that is dependent on two other pi groups? So Darcy friction factor is dependent on the first pi group, which is pipe characteristics, second characteristics being flow characteristics. So those two terms working in tandem will give you that third pi group, which is what we're interested in. Let's start with the first one, pipe characteristics. That's what you start with. We're told that we're working with cast iron pipe. I'll have this table later. It's table 6.1, but that table basically says with this type of interior or this type of pipe, either material or how it's finished, you will have this roughness value, and roughness refers to as epsilon. So basically, you have pipe and inside pipe, based on the finish, you have some kind of like bumps based on like the structure, and those bumps have the ability to basically trip the flow and cause the flow to be turbulent. And the mean of I think all those bumps would give you epsilon. That's like the mean height of those bumps. Anyways, for a cast iron pipe, epsilon is about 0.26 millimeters. Our pipe was 200 millimeters. Therefore, our roughness ratio of epsilon over D is equal to 0.26 millimeters over 200 millimeters, which then gives me 0.013. Sorry, 0.0013. Anyways, so that's our first pipe group. Second pipe group, flow characteristics. I'm referring to Reynolds number. That's what I'm talking about. That tells me my flow characteristics. So Reynolds numbers for pipe, RED, is rho VD over mu. But in our expression, it'll just be VD over nu. So V is 6.366 meters per second times D, which is 0.2 meters, divided by nu, which was 0.00001 meters squared per second. Therefore, Reynolds number is going to come out to be 128,000, which obviously is greater than 2,300, which means our flow is definitely turbulent. All right, let's pull up Reynolds number. Let's pull up the Moody flow chart and talk about that for a bit. First things first. Do you remember how I said in laminar flow we can have a simpler expression for head loss because Darcy friction factor is just 64 over Reynolds number? As you see, in the laminar region, this is true. That straight line can be expressed as the following: 64 over Reynolds number. That's why, while yes, you can use the Moody flow chart to solve for laminar problems, you can also just substitute the expression in, which is much easier. But you can always use Moody flow chart. It's always here. It's applicable for both cases: laminar, transition, turbulent. Okay. So early in the problem, we solved that epsilon over D, the pipe characteristics roughness ratio, that was 0.0013. So that means that our point, and so that pi term, basically, in terms of Moody flowchart, that is kind of like a family of functions. So based on that value, you have a different function to represent that pipe characteristics. And so our pipe characteristics is between the families of 0.001 and 0.002. Therefore, our function, I expect, looks something like this. Somewhere between those two lines. It looks a little skewed and bad, but that's what it should look like. Yes?
When reading the Moody charts, it kind of seems like you're giving your best guesstimate on where this is.
Yep.
Maybe marked off if we're like slightly off on like the final or something like that, or no?
Not at all. Watch this. I'm going to be really off, or a little bit off, and I'll still give myself full credit.
Perfect.
All right. So once again, yes.
So let me see if I get this right. You start at where the roughness ratio is, and then you just follow the same curvature to the transition.
Until you get your Reynolds number.
Basically, I just want to recreate my family of function because I don't have it here. If it was one of these lines, I'll just follow it. Yes. Based on that pipe, that line represents, based on what flow is going through it, that's to be your associated friction value. So that's correct, sorry. You are along that line. And I have to make my own line because my family of function was not listed here. Does that make sense?
Yeah.
Okay. Reynolds number, 128,000-ish. That's between 10 to the power 5 and 2 times 10 to the power 5. So between here, between here and here. I'm gonna make a guess. I'm probably somewhere around here. And as you see, I then intersect my other pi group. So my Reynolds pi group, my flow characteristics pi group interacts with my pipe characteristics pi group. And at the intersection, I'm not gonna draw a line over. Because then I can find my associated friction factor. So if you were to give a Moody flowchart problem in the final, you would follow some kind of process like this. And usually, if you guys remember, I had to iterate. Last week, I had to do the iteration process. However, in this section, my function here, h of f equals fl over d times v squared over 2g. I'm only missing f in this function. I'm not missing another variable. Earlier, or last week, I was missing v too. So I had f missing, I had v missing. Both are unknown. That's why I have to iterate until both values basically complement each other. But in this case, I have v through flow rate. Therefore, don't have to deal with that. As you see here, I obtained an f value of 0.024. The actual f value that you're supposed to get is 0.0225. So I was close, but not the exact. Still get full credit though, because I showed my work, obviously. The intersection of two pi groups gives me the net value. That's what I'm working with. Okay, back to the head loss equation. So F times L over D times velocity head is then just 0.0225 times L, 500 meters, I believe, divided by diameter of 0.2 meters, or is it? Yeah. Times velocity, 6.366 meters per second squared divided by 2 g's, 2 times 9.8 meters per second squared. This gives me a head loss of 117 meters. So that's part A, finding head loss, which via flow chart. Now part B, I want to find the pressure difference which drives the flow of this pipe. And the pipe schematic looks something like this. I'm also given an additional information of detail. I'm given the pipe has a 10-degree downward slope. So I'm looking for delta P, and the equation that I can recall that involves pressure terms would be, as stated earlier, the energy equation. So let me write that down one more time. P over rho G plus my velocity head term plus height equals pressure term, velocity head term, height plus head loss minus work by pump plus work by turbine. Okay. In this problem, this pipe flow, the flow, of course, pressure difference drives the flow, but also the flow is occurring due to the fact that there's a height difference. The oil is just sliding down the pipe. It's kind of like a slide. There's no pump or, there's no pump or turbine needed, so those two turbines go away. As you see here, I'm gonna set my datum at 0.2. I usually set datum at the lowest location. That just makes it easier for me. Therefore, the other one would be a positive value. Yes.
What's theta?
Theta refers to the pipe is sloped down by 10 degrees. So it's this term here. Yeah, so just saying that our pipe has a downward slope. That's what I'm saying. But yeah, 0.2 is datum. So 0 is here. So in this case, as I said earlier, or we solved earlier, Reynolds number was higher than critical, therefore working with turbulent flow. Turbulent flow implies that alpha will be equal to 1. About 1. Okay. But in this case, it doesn't matter because we have constant volumetric flow rate. Therefore, or constant volumetric flow rate, and also the pipe we have constant cross-sectional area. Therefore, velocity is the same at both locations. So these two just cancel out due to having the same Q value. And these pressure terms we can't cancel out. Pressure difference is driving the flow. We need those two terms. Okay, let me write this expression. So I have P1 over rho G plus Z1 is equal to P2 over rho G plus H of F. So, once again, pressure difference drives the flow. Flow goes from highest pressure to lowest pressure. Our flow is going from point 1 to point 2. Therefore, P1 is higher than P2. So I want to solve for P1 minus P2. That's the pressure difference I want to solve for. P1 minus P2 over rho G is equal to head loss minus Z1. So we have every term but Z1. So Z1's the height here. How can we solve for this? Well, we're given an angle here, and we see that this here is actually just a right triangle. Therefore, we can actually solve for delta Z. Delta Z is opposite from our angle, and we have our hypotenuse, which is the length of the pipe. Therefore, we can use sine of 10 degrees to solve for this system. So sine of 10 degrees is equal to delta Z, which is Z1 over L, which means that Z1, which is delta Z, is L times sine 10 degrees. Taking this expression, substituting it in, I get that delta P, change in pressure, is equal to specific weight times head loss minus L sine 10 degrees. So that's about 900 kilograms per cubic meter times 9.8 meters per second squared times 117 meters minus 500 meters times sine of 10 degrees. Which then gives me a pressure difference of 266 kilopascals. Any questions about that? Okay. Yes.
Do we assume this is fully developed? Is that the reason why the velocity is present?
Oh no. Fully developed would mean alpha equals 2, by the way. Oh, sorry. Well, yeah, flow is fully developed, but the reason I crossed it out is because both of them have matching Q values, or volumetric flow rate. Even if it wasn't developed, I think Q should be the same still, right? But that's not the reason why I crossed it out. Okay. If not, let's go to the next problem. This next problem. So basically, we have water of these properties flowing through a reservoir. So we're given density and dynamic viscosity. And it's pumped between two reservoirs at the volumetric flow rate of 0.2 cubic feet per second. We're given that the total pipe length that it flows through is 400 feet, and the diameter is 2 inches. 2 inches is the same as 2 over 12 feet. And of course, as we're flowing along the pipe, there is going to be roughness. There's some roughness, so there's going to be friction factor, as given by this ratio here. And once again, seeing epsilon cues me into the fact that it's probably turbulent flow. But obviously, there's head loss or friction loss due to the fluid interacting with the pipe itself. However, there's also additional losses occurring. These are called minor losses. Interactions with the open globe valves, or your bed, or these bend radiuses, or this half-open gate valve, or these entrances and exits. There's going to be loss occurring, and these losses are usually determined experimentally, or just like by running running much experiments and getting this average value to determine these kind of losses. And I'll talk more about that when I write my expressions. So once again, I'm assuming turbulent flow due to the fact that I work with epsilon. Okay, so I want to find pump horsepower. Okay, so pump horsepower, which is based on HP, that is part of the energy equation. Let me write that out first. All right, so HF, that's referring to just, us flowing through the pipe and interacting with the wall. However, these special components that are common and typically used when working with pipe engineering problems, you would encounter minor losses, which is referred to delta K, which refers to the different coefficients of the different components we're working with, all summed together, multiplied by velocity head, and that's the minor loss. These are minor losses due to the different components. Obviously, we have minus pump plus turbo. Okay. So let's talk about the K value first. So based on different components, we experimentally determine these K values, these K coefficients that are associated with these different components, obviously. So different components have different K values. The only two I want to point out is open globe valve and the half-closed gate valve, which have a high K value of 6.9 and 3.8. Basically, those two components, as shown at the start and end of that whole flow, is such as these materials. I think, imagine if there's a pipe and there's a valve. You're basically kind of screwing a valve into the pipe, and basically you're basically obstructing the flow. You're putting down an object to obstruct the flow. That's the purpose of these two components. So obviously, when we construct a flow, there's going to be some greater loss terms, obviously, right? Because there's now like a material in the way of the flow. So that's why we have high K values associated with those two components, as compared to like just bends in the radius or entrance exits. So sum all these terms together, we get a total K of 13.4, which we'll then use later on. For now, or jump back to our equation, let's cancel out some terms. There's a pump, but there's no turbine. Oh, sorry. In the problem, we're actually given our z values too. Forgot about that. But taking our starting location at the top of these reservoirs, two things happen. In the reservoir, obviously, that's hydrostatics, stagnant flow. These terms cancel out. Similarly, both are exposed to the atmosphere. So these terms cancel out. Therefore, our expression reduces to the following. Z1 is equal to 2 plus h of f plus delta k, or sorry, sigma k times velocity head minus pump. So we have basically all these variables that we're interested in. I'll solve for v right now. V is just volumetric flow rate divided by A. That is 0.2 cubic feet per second divided by pi over 4 times diameter squared. I get 9.17 meters per second. Feet per second, sorry. Okay, and the reason why this is important as well is because we also need to solve for Reynolds number to determine if we have turbulent flow. So, Reynolds number is, well, rho VD over mu, obviously, but we have nu, so it'll be VD over nu. So, 9.17 feet per second times diameter, 2 over 12 feet, divided by nu, 0.000011 square feet per second. That gives me a Reynolds number of 139,000. Obviously, that's turbulent flow. Now, h of f. Because our Reynolds number is turbulent, or it shows we're in a turbulent regime, h of f, we have to use the general expression of f times L over d times velocity head. So f, we have one pi group, which is flow characteristics. We have our second pi group, which is pipe characteristics, rough ratio of 0.001. Using Moody flow chart, we can solve for f. Okay, so let's go through the process again. I'm working with a rough ratio of 0.001, right? So that means I'm along this line here. Okay, so along that line right there. I'm Reynolds number, 139,000. So obviously I'm between 10 to the power 5 and 2 times 10 to the power 5. So I'm between these 2 points once again, but I'm slightly a little more further down, I guess. So somewhere like around here, maybe. And as you see, I intersect right there. Draw a line over. I get an F value that is about 0.022. Am I right? I'm close. The actual answer should be 0.0216. All right, so using this term, I am now going to, not move the flow chart. I'm going to rewrite my expression for head loss here and plug in my related terms. So I think we're 400 meters of pipe length long. So remember, this is just friction effect due to us flowing through the pipe. There's no, the minor losses we already accounted for, this is a separate thing. Yes?
On the final, we'll just go with whatever we estimated, right?
That's correct. Don't worry about as long as you show me how you got the 2 pipe groups intersection, you're good. Diameter, 2 over 12 feet. Head, velocity head, 9.17 feet, this feet per second. 2 G's, which is 32.2 feet per second squared. You'll get a head loss of I think it should be, yeah, 67.7 feet. Back to our final expression, not final expression, but our initial expression, Z1 equals Z2 plus HF, it's delta K, E squared over 2Gs minus HP. We want to solve for HP, because we want to solve for the pump work required. This is equal to delta Z plus head loss plus delta K, E squared over 2G. Delta Z, 120 minus 20 feet, 100 feet, plus H of F, 7.7 feet, plus delta K, which is 13.4, when everything's summed together, times velocity head, so 19.17 feet per second squared, divided by 2 times 32.2 feet per second squared. Overall, HP is equal to 185 feet. And that sounds like, that's like fluid column height associated with the pump. So to convert this to power of pump is then equal to gamma, specific weight, times Q times HP. Gamma is rho times G, which is it's water. So honestly, I remember, so gamma water is like 62.4 pound force per cubic feet times Q. Q being 0.2 cubic feet per second. HP, 185 feet. Overall, power of pump is going to come out to be 2,300 pound force per feet per second. I want to turn it to horsepower, so I divide by 550. So that's 1 horsepower is 550 pound force per feet per second, which then gives me horsepower. 4.2 horsepower is required to pump the water through that system, basically doing all the loss, move the water to a higher location, and deal with friction losses, these minor losses or along the pipe. And this is assuming our pump is 100% efficient as well. Any questions on that process? Okay, we're almost done. Let's go to our last problem. I'm gonna try to speed up for this, but there is a gutter system. I mean, I guess we've seen this before. And in this gutter system, it's similar to problem 1, where the top half, this section is kind of like the reservoir. And this bottom section, this is like the pipe flow stuff that we've been dealing with. So heads up. All right. So for water, same property as before. Water properties are 998 kilograms per cubic meter. Viscosity is about 0.00 newtons per meter squared times second. Okay, but in terms of additional information, we're told that pipe length 20 centimeters, so 0.2 meters. Pipe diameter, it says 2 millimeters, 0.002 meters. And we're interested in finding rate of draining, as you see. If the pipe was fully full of water, what is rate of draining? So once again, as I said, similar to problem 1. We're not giving much information about, so we have rho, we have mu, we have d, but we don't have v. We're trying to solve for v, so we can't really get Reynolds number. So obviously, without Reynolds number, I can determine laminar or turbulent, but I'm not really giving information about pipe characteristics or anything like that, so it's probably gonna be laminar flow. That's my guess. I have to double check this guess later, but for now, assume laminar. Oh. Okay. Okay, so once again, I'm gonna treat this like the problem 1. Start with energy equation. This drainage system, there's no pump, there's no turbine, but there will be some kind of head loss. The top part, which is location 1, that's kind of the reservoir section I was talking about. Therefore, there's no velocity occurring, and both sides are exposed to atmospheric pressure. Okay, for the flow coming out, we assume laminar. So in this case, we're going to assume alpha is equal to 2. Last thing, we're going to assume location 2, which I'll note as 1 and 2 here. Location 3 is our theta. Therefore, Z2 is going to be 0, 2. So I simplify our expression to the following. Z1 is equal to, these two cancels out, so it's just V squared over 2G plus head loss. So we don't know V, we don't know F. Sorry, we don't know V, we don't know head loss, but assuming laminar, we get expression for head loss. Head loss is gonna be 32 mu L V over rho G D squared. So I'm gonna plug in relevant terms, which is like mu L V we don't have, but rho we have. G we have. And D we have. Head loss, therefore, you can simplify to become 0.1634 times V. I'm gonna get rid of units and I'll explain more in a bit. But substituting this F equation into this equation up here, Z1, that's 0.2 because that's the height of the overall system from point 2 to point 1. Second term, V squared. Oh wow, which is V squared over G. 1 over G should give you 0.051, and I'll keep the V squared here, plus our new term, which is the head loss, 0.1634 V. As you see, we have a quadratic equation. If I move this term over, I could solve via the quadratic formula. V is then equal to negative B plus minus square root of B squared minus 4 times A times C divided by 2 times A. I'm gonna get two answers, obviously, but one answer will not make sense. Negative velocity doesn't make sense because we're saying that the drainage system is shooting out velocity up through the top. That doesn't make sense. We're gonna take the positive value. Positive value would be a draining velocity of 0.945 meters per second. Okay, and so that's the velocity exiting our pipe if the gutter is fully full. Drain rate is volumetric flow rate. Therefore, the drain rate is gonna be V times cross-sectional area. So we have our draining rate times pi over 4 times D squared, 0.002 meters squared. And you're gonna get a Q value, drain rate, of 2.97 times 10 to the power of -6 cubic meters per second. That's the amount of water being drained out if we treat that system kind of like problem 1, reservoir and then pipe, fully filled. Last thing, we made a laminar assumption. Let's double check. And I'm going to write these terms down. And as a result, Reynolds number is going to be 1,890, less than critical number. We're good. Problem is good. Any questions on that? If not, last problem, and we're done. Last problem. Now, this problem, we have two reservoirs on stacked top of each other. Think of it as like a chocolate fondue fountain. That's how I think of this problem. Top reservoir, there's liquid flowing down, flowing down to the second reservoir. And basically, we're trying to figure out what the flow rate is through this pipe. So, most of the things we're given are geometry-based properties, but we're given that we're working with ethanol alcohol. So, we can talk about that more in a bit. Here. So, ethanol will have the following properties. Rho of 789 kilograms per cubic meter. We also have a viscosity of 0.0012 newtons per second per meter squared. And diameter is shown here, 0.002 meters. Last thing about this, Q is flow. We're trying to solve for flow rate, right? Obviously, there's two reservoirs. Reservoirs are going to be hydrostatics. There's no motions going on. The only place where flow is occurring is through that pipe. So the properties I'm going to write down here are based on the pipe. So diameter of pipe, obviously, is 0.002 meters. One more thing I want to mention is length of pipe, because that's going to be really important for us later on in the problem. So obviously this whole contraption has a different bunch of the change in z values, but length of the pipe is only where the pipe is, and pipe starts here, pipe ends here. Therefore, length of pipe is 40 centimeters plus 80 centimeters. So it's the exposed surface plus the surface submerged in the second reservoir, but not all the way to the bottom of the reservoir, just the section of the pipe. So length of pipe is 1.2 meters. Yeah. Okay, we're trying to solve for flow rate. Flow rate we can obtain through many ways, but I guess finding velocity is probably one of them, right? Where can we find velocity? Let's look at the energy equation. And I probably should mention, given like barely any information, let's assume laminar flow too. So, total energy plus kinetic energy plus potential energy is equal to total energy plus kinetic energy plus potential energy plus head loss minus pump work plus turbine work. So, in this problem, there's no pump, there's no turbine. The two locations I've picked, as shown here, those are the two locations. These two locations have are in like the reservoir region, so there it's hydrostatics. Therefore, these terms cancel out. Pressure, both exposed to atmosphere, both going to cancel out. Height values, I'm gonna call this my datum. Therefore, Z2 cancels out, and Z1 will be 40 plus 50 centimeters, so 0.9 meters. My final simplified expression is Z1, which by the way was 0.9 meters, is equal to head loss. So very simple expression in the end. Head loss, assuming laminar flow, we have the following expression: 32 mu L V over rho G D squared. I want to solve for Q, and obviously Q and V are related, as we talked about. Q is just V times A, right? So that by that, therefore, V is Q over A. I'm going to plug this expression into here. Therefore, I'm going to get head loss to be expressed as 32 mu L times Q over pi over 4 D squared. Obviously, because I plugged in Q over A for V over rho G D squared. Simplifying these math, I'm going to get 128 times mu L Q divided by pi rho G D to the power 4. And this is an expression that I think you've seen in class before. It's just me plugging that term. Now I'm going to solve for Q because I have every other term. I have mu, I have L, I have rho, I have G, I have D. Take the reciprocal of all these coefficients, move it over to the other side. Q is equal to pi rho G D to the power 4 over 128 mu L times Z1. So Q is equal to pi Z 198 kilograms per cubic meter times gravity 9.8 meters per second squared. D 0.002 meters to the power 4 divided by 128 times mu 0.0012 kilograms per meters per second times L 1.2 meters times Z 0.9 meters gives me a Q of 1.0 or 90 times 10 to the power of negative 6 cubic meters squared. So this term, you can solve for V again if you want to, but for me, I'm just going to keep it as Q. Reynolds number, because once again, we assume laminar, gotta double check. Rho V D over mu, V, Q over A once again. So mu, or rho times Q over pi over 4 D squared. D, over mu. Reynolds number can be expressed as rho Q D, put a 4 there, bring the pi down. Sorry, gotta bring the D down too. So D over D squared is 1 over D. Then 1 over D gets sent down to the denominator. Here's my expression. Plug in my variables of interest. I specify this is wrong here. We're working with ethanol. Remember that. We're working with ethanol. Volumetric flow rate. Pi times viscosity, 0.0012 kilograms per meters per second, times diameter, 0.002 meters. This gives me a Reynolds number of 795, therefore obviously less than the critical number. We're good. This problem checks out and we've solved for the Q value. Any questions about that? Bit long process, but you see all these equations I've used, we've used it over and over again. I think my main takeaway is h of f has general expression. General expression relies on Darcy friction factor. However, with laminar flow, the equation becomes much simpler because we can express f as an actual function of Reynolds number. That's what makes this process so much easier in laminar flow. Otherwise, moody flow chart. Thanks for coming. That's the last discussion.